this morning to start with Paola Iannone from University of Edinburgh, who has a deep history in lean, both in formalizing mathematics and in mathematics education. And my very light understanding of the genesis of this goes back to a fortuitous meeting with Kevin Buzzard, perhaps at an LMS meeting, and then as early as 2019, I believe you were already working on lean for teaching undergraduates. And among other things, Paula is also an editor-in-chief of the Journal of Research in Undergraduate Mathematics Education. Did I say that right?
Yep.
And so a fantastic person leading the charge in bringing lean and formalized mathematics to teaching. And we're going to hear about that and more today. So,
okay, so thank you for having me today. I think that the idea of this talk is to share both where we are in terms of research regarding the use of lean in undergraduate mathematics, but also to share some of the tools and the methods that we use to do such research. So in this talk today, I want to present some of the questions that we ask when we do research in mathematics, and I want to discuss some of the theoretical tools that we use to investigate this question. I will then share some results. As always in education, we don't have all the answers. All the answers are still out there, but we know a little bit. And then I will finish with some ideas for future research, which I think are important and we should go for. So let's start. There is a problem with students coming into the first year. We all know that this is an issue. Everybody who's taught first-year courses knows this. Personally, I marked about 700 scripts last year in a calculus course, and a lot of the students were trying to convince me that 4 is equal to -4, which is really interesting when it comes out on a first-year calculus course. There are huge problems with students approaching the mathematics that we want them to do in the ways that we want them to do it in the first year of university mathematics, even if they come to the university with very high grades at school. And this is a well-known problem in mathematics education and something that has been studied quite a lot. The reason why I put my favorite comics here is I just want to point out that actually the issue is not all with the students. There is also a little bit of an issue in how we teach them. But this is not going to be the subject of this talk. Just a little reminder. So, if I had to have £1 for every time a colleague of mine in the department told me students don't understand proof, then I would be rich and I would be somewhere in the sun that is more sunny than this, probably. The issue with thinking the students cannot understand proof is that this is a badly defined question. What do we mean when we say the students don't understand proof? So my thinking around proof has arrived to this class of difficulties. So it's not only my thinking, as you can see, this is like a large field of work in the literature where this belongs. So we can talk about epistemological difficulties. When students arrive in the first year, they don't really know the role of proof in pure mathematics because nobody has told them. And so we have conversations like, I know square root of 2 is irrational. You know square root of 2 is irrational. Why do I need to prove it? And so we talk about necessity, like constructing this necessity for proof, right? There are difficulties with proof comprehension. So how well do students understand the proof which are presented? We know from research that often, in the best of the cases, students focus on the transition of line by line, but they don't focus on the general idea of the proof. So there is research around this done both with qualitative methods, but more recently employing eye tracking techniques. So we know the students look at line and then the following line, but if they were asked what's the key idea of the proof, they wouldn't know. There are big issues about proof writing. There is a very good study by Kirsten Lowe and Pablo Ramos at Rutgers University, who show that students and lecturers don't share the same understanding on what constitutes an academic style of writing a proof. And this is really quite interesting. The study has a lot of really nice examples that show this. There is an issue with proof appraisal because students have difficulty with proof comprehension, but also because all the proofs the students see in the beginning of their undergraduate degree are correct proofs are given to them by the teacher, they are not able to then understand whether a proof is correct or not. And a lot of the time, they don't even ask themselves the question. They just think is this correct because the teacher said that that's true. And this then transferred to other proof they may see. And finally, there is this idea of proof composition. So how do you actually put a proof together? If you like, this is the oldest field of research in this area. Started off in the 80s with the work of David Toll and carried on to today. And among the difficulties, we have the students don't understand the definitions, don't know how to structure the proof, cannot divide the proof in parcels, if you like, in goals and sub-goals, and they don't know how to put this together. In this talk, I'm trying to see, if you like, where Lean could help in these fields, and where we think it maybe cannot help, or we don't yet know that it can help. So, in the classroom, Lean is used in two different ways. There are now quite a bit of courses at advanced level, fourth year, PhD, master's level, that aim at training the mathematicians of the future, that aim at teaching the mathematicians Lean, because they would like to use this in their research, or rather, the person who's teaching would like them to use it in their research. And there are issues and there are examples of Lean in a transition to proof courses. This is something that we borrow from the American way of saying. By this, we mean courses in the first year that are aimed at familiarizing students with the convention of undergraduate mathematics, and this typically involve proof and so on. And of these courses, there are courses that use Lean programming and courses that use interfaces like Waterproof or Limberbos. My work has been on this side. It's been on courses that use Lean for programming. The conversation about what is best to do is so open, and each one of these two implementations gives you different things. So for now, I focused on this one, but I think the other one is just as important. So what is the idea? The idea is that if I get a student to interact with the interface like Lean, they will acquire certain skills that are also to do with programming or with the structure of Lean. So for example, divided proof in goals and sub-goal, precisely of kind of being precise in the language, because this is obviously a computer program, so it's not, the syntax is not precise, it's not working. And the big question is, do the skills acquired while learning Lean transfer to doing proofs on pen and paper? Because I think that the big idea at the start of a university degree is that we would like students still to do proofs on pen and paper. And we want this to be a help. So let's see what we can do. Now this slide I did on Wednesday, last Wednesday. Every time I look in the Lean community, there are more courses registered that use Lean, and I've stopped looking. So if you go in the Lean community, the numbers will be different. But this is just telling me that there is a lot of interest in this, and therefore it seems reasonable to ask oneself whether this is supportive to learning, and what this interaction does that we want it to do. So these are some of the current research directions that there are. It's important to understand what are the affordances of each different interactive theorem prover. We call this an a priori analysis, because different theorem provers can do different things and interact differently with students. There is the issue of transfer, which I'm talking about. There is the issue of technical language. There is an epistemological issue. Do theorem provers help students understanding the necessity for proof? There are difficulties with programming languages. And then there is the issue of resources, which maybe I'll talk for a moment at the end. For now, I want to talk about these three fields. A priori analysis. This is the work of a group in Paris, led by Iro Bartiza. And what they have done, they have given Roch, Isabel, Educara, Deduction, and Lurch these tasks, and they have analyzed the process, investigating how the language interaction works, how the automation and the user assistance work, and how the proof structure and visualization work in the different theorem provers. So it's too long to summarize the results. This is not the kind of study where you say this is better than that. It always depends on what you want to do. So if you're interested, you can read the paper. But this kind of analysis is important because ultimately, as a teacher, I will have to choose a tool, and I need to know how it works. The issue of transfer has been looked at in many studies, well, not in many studies, at least 2 studies, let's say. This is still a small community. So in 2024, Hannah, Larber, and Jan observed 3 students while they were engaged with Lean. So they structured the workshop and they recorded the screencasts and the interviews, and they took task-based interviews. And amongst the things that they found was that using this system did not stifle students' creativity. So there was an idea that because you need to put something very precisely into an interface, this could kill the creative aspect of mathematics. So from their data, their tentative results is that this is not the case. But they didn't really look at transfer very much. The issue of transfer is what Atina Thoma, who is my previous PhD student currently at Southampton University and has done this work with me since day 0, we investigated exactly this issue. So we did a study which was a bit complex. I'm not going to say everything that we did because it's too long. But the bit which is interesting is that we gave 37 students this proof to do. The task, as you see on the board, in the context of task-based interviews, and we recorded the written work and the dialogue that was going on. In order to be this student belonged to a transition to proof class that had Lean as a voluntary aspect, if you like. So it wasn't compulsory to engage with Lean, but it had it there if the students wanted to. In order to be able to understand whether proof looked different, whether it was a Lean user and a non-Lean user, we gave all the proof to appraise to a mathematician that knew nothing about the course or the study or anything. They just were experienced in marking first-year work. And what we did, we then compared proof at the same marking levels. Proof that were deemed to be correct or proof that were deemed to be not correct. We didn't have just correct and non-correct. We have marks from 1 to 4 in order to be able to kind of get the details. So what did we find? Before we speak about what we found, we need to think about what we're looking for, right? What does it mean? I want to see how the proof look like. What are the things that we need to look for? There are various frameworks that help us in mathematics. The one we used was the one by Fuhava Connolly. And this framework tells us something that we need to see if I want to say that proof comprehension and proof composition are fine, right? That there is an impact and that this works well. These things are things that I think everybody will know: meanings of term, logical set of statements, the idea that if you have lines of proof, it would be nice if one followed from the other. This idea that students are able to understand the high-level ideas and understand the modular structure of the proof, to transfer ideas to another context and use examples illustratively and also to convince themselves of the kind of status of the statement. So we deployed this framework, we analyzed all our data, and this is what we found. So this is a sample of 2 successful proofs, the start of 2 successful proofs from the statement you've seen before. This proof looked different. So if you look at the way in which mathematical language is used, we observed that in students who engaged with Lean, we found complete sentences down to punctuation, which I had never seen marking first-year courses, like really never. Students who completed the proof correctly, that didn't and had not engaged with Lean, that didn't have the same level of preciseness in their mathematical language. The other thing that we saw from unsuccessful proofs. In here you have the writing of the students and the transcript of the interview, and the one in parentheses, please forget it is our coding, okay, according to the framework you've seen before. For this, for example, we can see that the students has an idea, but they're really struggling to put it on paper, so they really cannot do that. So they may have an idea of how things go, but it's just not working. And this is a non-Lean user. But even with Lean users, there were students who didn't manage to finish this proof. And what we noticed is that they tried to deploy a very heavy syntactic language that it just really wasn't needed here. So look at this student. So he's trying to use the Iverson bracket to solve something which is fairly easy. And in line 24, it just goes, I need to formalize this mess. This is not conducive to writing particularly good proofs at this level. So what did we find in the end? We found that the impact of using Lean in this context was mostly on two aspects, on the writing, so on the mathematical language. We did notice that students that used Lean were better at writing than students that did not use Lean. And that they really were more precise in saying, like in declaring where object belonged to, right? So if X is a real number or whatever. We also noticed that they were better at parceling up the proof in goals and sub-goals, and this we can reconduct to Lean quite easily. So that's great, but we didn't see in the interviews, although the interviews were carried out on pen and paper, so we didn't have Lean, the students were not writing code, we just gave them a task and we said, off you go. We saw that there was very, very few students used examples. And we know that using an example in the beginning, if you don't know what to do, is a very good thing, right? So you get your head around how these things may go. But we didn't see this. We know that this activity is difficult for students, but we do wonder whether engagement with this platform, with Lean, at least how it was done at the time, could stifle this a little bit. Lean is not great for saying, oh, I'll just do 2 prime numbers here by the side and see what happens. And there is some more work, more recent, by Bottoni et al. That is making more or less the same argument. And of course, we had this idea that formalization sometimes got in the way. So this is how we are. The second thing that we looked at are the issues with programming language. So learning to code Lean is more or less learning a programming language. For this, we looked at the computer science literature and the classification by Kian and Lemon, and we did find all the kind of area they suggest. We have conceptual difficulties, syntactic difficulty, and strategic difficulties. Although we don't really quite understand yet what is in this strategic and conceptual difficulties when the software is Lean and is used to solve a mathematical problem, there are studies at the moment that are trying to look into that. And if we knew this, then we would know how to support the students maybe overcoming these problems. By the side here, I have examples from our data. These are all utterances from students, which we have classified in this way. The other thing that was a surprise to us is that when the students talked to us about this programming language, about Lean, they had very strong affective reactions. I mean, they were polarized between, this is fun, I want to do this for all my life, and I don't want to see this ever again in my life, please take it away from me. Affective reactions are really important in learning, so we cannot just dismiss them. And this was also quite surprising. The other thing that was quite surprising, not very many, but some students told us that this idea of being explained how mathematics is built up from the axioms helped them understanding the role of proof. Right, and this is quite important, it's the epistemological aspect. However, a lot of the students did not see the link between this programming activity and pure mathematics. The reasons why this is the case, and actually I'm collecting some data with my PhD students as we speak, and this is coming out again, is because in university mathematics, we use programming mostly for mathematical modeling and for large computations, basically, but not really as linked to pure mathematics. Okay, so this was the first thing we did, summarizing. We need to think that different ITPs have different affordances and different characteristics. There is still a lot to learn about transfer, so we really don't quite know what happens there and what happens to the areas, for example, of proof comprehension, of proof appraisal. That's not quite clear. We aren't really sure of the impact on Lean, on intuition, and for example, on intuition and for example, and on example use. And we need to think about the difficulties of learning Lean itself, right? So if you are talking to first-year students, this will have maybe some programming experience, but not that much. What about Lean clubs? One of the things that interests me most is that there is a lot of very young mathematicians, students in their first year, that are interested in Lean, even without this being mentioned by their teachers or without being told that this is a thing. And there are these Lean clubs that come out spontaneously. We have one at Edinburgh. I don't know whether Alex is here, but Alex is the one who started the one at Edinburgh, is in this meeting today. So what we thought with my colleague was, wait, is this enough? So would this be okay for students to learn, to kind of support them also in their mathematical learning? After all, you construct a natural number, you have this idea of axioms, you can play with the language and all this kind of stuff. So we did a study, as one does, and we looked at this study in this way. So what is the activity? So student sits in front of the natural number game. The idea is that you have an interaction between a tool and a human to achieve a goal. So the tool being Lynn, the human being the student, and the goal being writing the proof that you want to write. Now this is a really common situation that's been studied to death in a lot of areas of not just mathematics education. The other thing which is interesting is that when students say arrive to, at some point in their first year, but also maybe a little bit before, they are familiar about achieving the same goal with a different tool. So they've thought about producing a proof in pen and paper, so having the goal of the proof, interacting with the tool of pen and paper, and producing. So how do these things blend together, and how does knowledge construction, and how is knowledge construction affected by the mediation of a tool? This is the idea. In order to do this, we used this other idea, which is interesting. Rabardel came up with this theoretical framework that comes from the work of Vygotsky. And he came up with this for interaction with tools in the workplace, which is really interesting. But it has been used in mathematics education. So we call this the instrumental approach. The instrumental approach distinguishes between a tool, in our case is Lean, and it's a physical tool. It could be Lean, but it could be something else. I'll give an example later. And an instrument, which is the psychological construct. And by determining this instrumental genesis, we are able to distinguish between productive and non-productive Lean use. This is the picture, right? So the picture is that you have a student on one side, they've learned how to do the proofs, maybe not very well, but they have some ideas of what they need to do in that medium. We give them another medium, and now we have an instrument. Now, the idea of the instrumental genesis is that what I call the construction of knowledge, or I could also call learning here, happens in completely different ways than what happens up there. So what are the ways? What did we do? Oh, no, before we do this, these ways are described in what we call schema. So think about this. You sit in front of Lynn, you look at the interface, you do something, right? So you write a line of code. You have written a line of code for certain reasons, so you don't choose your code random. And this is the schema. The action you make, the reasons for which you make it, and the ideas behind the reasons you make it form this schema. It turns out that these things are fairly stable for the same activity, of course. So when people acquire some of these schemas, then they kind of carry on, right? And in these schemas, we have rules of action, concepts in actions, and these put together give us computational aspects, so the possibility of inference, the possibility of doing something. If I want to see this in a graph, I often think better with pictures. We have the interactions, and the human does something, and this is the generative aspect. These rules of action are motivated by theorems in actions. Terrible name. These are not just mathematical theorem. They could be anything that the person seems through. I did not put together the framework. If I had, I would choose another name, but there you are. And these theorems in action are justified by things that the person seems understands to be relevant, which are the concept in action. These are the epistemic aspects, and these three things together allow us to make inferences, to carry on. So how do we use this in real life? I've talked to you about this idea of knowing how to do something with a tool, but knowing how to do it with another tool as well. It's the same of this situation. I've learned how to type on a typewriter. Somebody gives me a word processor. How do I rearrange my ways of acting to achieve the same goal? If you think about this, this is the same situation of the students. Right. So In the Lean clubs, at least the one at Edinburgh, the first thing that the students did, they engaged with a natural number game. This is the entrance to Lean for, I think, nearly everybody. So we wondered what was happening in this engagement. So what was happening to the interaction between the schema that the students had constructed before to write proofs and the ones they now do for interacting with Lean, and what happens? Is the situation better for learning mathematics, or is not, or what? This way of reasoning was, in mathematics education, was brought in by Trush in 2005, when graphic calculators became available in schools, and there was a major panic, nearly like the panic we have about generative AI at the moment. And scholars suddenly said, okay, wait, we need to understand how this works, right? So we are just kind of redeploying the same tools for a different situation. So this is our study. We interviewed 4 students for a total of 70 hours. I can guarantee you the 70 hours of interviews are a very long time of interviews to look at. And we wanted to understand what were the schemes that were generated by the students, basically, so in the interaction with Lean. The thing that caught our eyes first is that, in a way, in Lean, you can make 3 types of error. Right? You can have a static error, that's fine, you forgot a comma, something. You can make a logic error, so something is not in a type or is not in the type you want. But there are these context, I call them error, they are really quite error, where your reasoning is correct, but it's just taking you somewhere that is not where you want to be. So our aim for the study was, does unsupported interaction with Lean help learning how to write proofs in pen and paper? Easy. What did we find? So I want to show you findings from 2 students here. And I want to show you these students because these are, if you like, the opposites that we got. I want also to say that these extracts that I'm going to show you are somewhere in the cycle. I think we interviewed this student for a total of 9 hours, and the students I'll show you next for a total of 12 hours, because we wanted to understand when this schema stabilized, right? So when the students repeated the same action. So look at what the students is doing. The students is doing this statement up top. It solves the statement in 3 lines, right? And then, that's disappointing. Can I redo the proof again? And it redoes the proof. This is really interesting. We called this schema the constant comparison with written proofs. In all the activity of the student that we monitored, this happened all the time. A lot of the time, he constantly compared, oh, but if I was writing this in pen and paper, then this is what I would do with Lean. And thinks about this, it says to us, there's another interview extract, which I haven't put here because otherwise I'll be still here tomorrow, that he calls the tactics the cheat way, right? Because the tactics obscure what is going on. Now think that these are students who just finished the first year. I don't know about you, but I tell my students that if they write a proof, at least at the very beginning of their education, I really want to see all the glorious details, right? Because that's the aim of the exercise. And here, these details are all hidden. In the activities of this student, we saw that Lean helped them checking the proof. And this was really interesting. So this was really a productive collaboration between the tool and the student to achieve something which is quite extraordinary. As I say, this is by no means the first time that the students look at this and say, I don't want to do it this way, I'm just going to do it another way. And how would it work? Another time, the students told us that writing the proof in Lean had helped them understanding how their thinking in writing a proof on pen and paper maybe had a small hole. This is really interesting because I've heard this in this conference several times of colleagues that now are doing formalization projects and are saying, oh yeah, wait, but I now understand this better. So this is one example. And this is how we describe the instrumentation scheme. So this is what the student done. We call this constant comparison with pen and paper. These are the actions, or some of the action that get performed. I write a line of code to see how it changes the goal pane. I compare what I do with what I do in pen and paper. I'm aware of the goals. This was really important. You always had an eye to the goal that was coming. Theorems in actions which are relevant. A proof are about explaining all the steps. If and only if proofs are 2-part. Automation, covers the steps of the proof, and this is why I wouldn't have called these theorems, because they're not all theorems, obviously. And in concept in action, we have, for example, the idea of if and only if proofs, which were the proofs that the students were trying to show. Now let's look at this other student. Now this student, same university, same class, same education, more or less, is doing what we say, playing the lean game. So the aim of the only goal that the student has is to close the proof. There is no really very much interest in what would happen in pen and paper. It's playing the game. It's guessing. At this point, it's still possible. Obviously, more advanced proof, this becomes not obvious anymore. But it's really playing, right? And we can see it in this transcript. So, oh, I'll do this, and then I'll see, oh, no, wait, they didn't like that. I'll do something else, and so on. He deploys tactics very often. I have a better extract than this, but it didn't fit on the slide, so apologies. And sometimes he knows that, so in another conversation, he was talking to us in another part of the interview, I was saying that I know that the tactic ring will close this goal, but I don't really know why. I just know that this is what happens. And as I said, this is the natural number game, right? It's nothing like the formalization things, projects we have seen here. So if you want to look at the instrumentals and the instrumentation of the students, the rule of actions look quite different. So there is this try idea. I try this, and if it doesn't work, I try something else. And if it doesn't work, I try something else. And he's not just trying blind. He knows what, more or less, I mean, he has an eye on what he needs to prove, but he's very happy to deploy the full automation of the interactive theorem prover and draws freely on resources from previous levels, which the other student didn't do that much. So the theorem in action, I can say the prior result can be deployed in coding, proof by induction as to goals. That was a proof by induction that we just seen before. The addition of the natural number is commutative. Trying out lines of code is okay, which we really didn't have before. And in the concept, we have induction, natural numbers, these things. So what do we want to say in the end from this study? Our hypothesis is that not all lean instrumentations are conducive to do better mathematics for the students, right? So just letting the students loose with lean and interacting with the natural numbers is not necessarily going to help them writing a good proof on pen and paper, if this is what we want to do. So we need to be a little bit careful in the way in which we use these tools in teaching. And the thing that we really need to do is to write and evaluate resources. And the evaluation bit is really important, because sometimes I go away and I write something and I say, this is going to be fantastic for my students, and it's a disaster because it actually really isn't. So evaluation is really an important part, and there are systems and tools that we use for evaluating educational resources. So I want to finish with some things that I think we should be doing and we are not quite doing yet. One is continue to investigate the impacts of systems like Waterproof. Jim is here somewhere, I know I've seen him, or Limber Bose, Patrick is here. So this is really important, and we really need to understand how these tools contribute to students' learning. We need to carry on investigation of courses that use bespoke lean material. There is a group in Paderborn in Germany, Irene Garnello and her PhD student, her supervisor, who are designing and implementing a series of resources. Irene will be the teacher of that course, and they will do an evaluation. We need to really understand a little bit better both this idea of what is in this basket of strategic and conceptual knowledge that students find difficult in lean, because if you understand this, then we can support them with the appropriate resources. And we really need to dig deeper in this idea of the interaction. This is what my PhD student, Chiara Van Cleen, is doing in Edinburgh, supervised by my colleague Atina Tama. And this is my next project. So this is a plug for my next project. I want to understand why mathematicians decide to deploy an enormous amount of time to use lean to teach first-year mathematics. And this is really important. So for me, this is really a surprise. I've worked collaboratively with mathematicians for more than I can want to say. And anything that requires time is not done. Understandably, I mean, this is not a criticism. I mean, if you came to me and say, do this thing that takes a lot of time for your teaching, I would say, oh, wait. But this is not happening. Why? And I think it's important to understand. And the plug is, if you teach a first-year course with Lean and you get an email from me in the next 2 or 3 months asking you to take part in a study, please say yes. And finally, I want to thank Kevin, because this is by this chance encounter that I got into this area of research. This is Atina Toma, my colleague at Southampton University, who works with me. We've done all these studies together. And I want to thank Guillermo Singh, a mathematician at Exeter University, who's also collaborated with us in our study. Thank you.
Thank you very much. We have good time for questions. Start with Jeremy.
So I was, at one point you mentioned the concern that when students learn to do mathematics with Lean, it suppresses their ability to think about examples or use examples. I mean, that's very interesting to me because, I mean, it's a well-recognized phenomenon that Lean is very good at, reasoning about very abstract things. But, when it comes to very concrete examples, it's much, I mean, so in his talk yesterday, Terry mentioned, being surprised that, running through measure theoretic inferences was straightforward, but then the kind of trivial concrete inferences. But it doesn't have to be that way. I mean, Lean has a computational engine. I mean, you can define, a number theoretic function and calculate values. We have widgets that will, let you display things in creative ways. So what that suggests to me is that for teaching, we should think about Lean not just writing proofs, but as an engine to let students create mathematical objects and display them and manipulate them and test their properties.
Yeah, absolutely. This is the idea of creating adequate teaching resources, right, to encompass all these areas. Yeah. In the study that I showed, which came from this curiosity to see what happened in these Lean clubs, this doesn't happen, but with appropriate resources, then maybe one can think about how do I incorporate this into my teaching, so how I help students kind of doing this. And using examples has been really one of the big thing in this idea of teaching students how to put proof together when it's not the proof that I've seen before. So the proof we gave the students was this very phony definition, which is completely useless in mathematics, which we used because there wasn't any mathematics in that definition that the students didn't know, but they wouldn't have seen this proof, right? So for them, that was a creative aspect, right? So they would have not seen this proof. They would not have said, oh, yeah, I've seen this proof. I remember how to do this. And so one could construct things that would help them in this way.
More questions? Kevin?
Can I draw a picture?
Yeah, sure.
You had a question about A as a subset of B, or so. F went from A to B. It's going backwards.
Oh, this one.
There.
Yeah, don't talk this not my study.
I see that I'm a first-year undergraduate, or I'm somebody teaching a first-year undergraduate, and I absolutely want to draw this picture. Right? There's A, and there's B, and here's the points in A, and here's some function. Then it's doing this, and that does that, and then there's another point here that doesn't get, right, I've got, it's something that's not injective, something that's not surjective, it's not bijective, and then I've got some C living in A, which is probably, I don't know what it is, maybe I need another, I mean, I'm trying to draw the right, maybe it's that, there, see, and then I've got to sort of try and understand the left-hand side and the right-hand side. And this is and then the second question, F is injective. There you have to draw another picture, and maybe the other picture now looks like this, right? B and A, right? That's probably a better picture of an injective function, and then C lives in here. And somehow for that second picture, that second question, once you've drawn this picture, the question's almost gone away. And now Jeremy's saying, oh, we have an evaluator, we have widgets. But like, how are you going to draw that picture?
But you are a really good undergraduate student.
but if I'm teaching them, now there's 5 more questions like that. Yeah, but
why can't there be a widget? Why can't there be a widget that draws
Venn diagrams?
Well, you want to have widgets that will let you do exactly that.
But whose job is it to make those widgets? Why don't we have those
It's
widgets?
ours. We can do that.
I think that
Mine. I'm trying to pre-formalize
I think that
That's my problem.
that there is something still to sort out in the community of what we want the interaction of Lean to do, right? So I started off from the point, which was the point in 2018, that we want this to support the proofwriting in pen and paper, right? So still we want students to be able to do proof in pen and paper, but we want them to be able to do them correctly and nicely and written in a way that I would recognize as a proof. Now, this is one level. And at this level, I think that picture is quicker, right? Do we want students to start reasoning and forgetting about the tool before and just using Lean? I don't know. Is this where we want to go? And then we need to think about, yeah, well, then this is what they need to do. Then we need to have
But I
interfaces.
want a widget that will let them do exactly that, and then start writing the proof.
Well, why does that have to be a widget? Can't it just be the instructor draws that on the blackboard and uses that as the impetus?
The nice thing about a widget is you can add points, you can move things, you can change things. You know, it's a word. It's a blackboard process.
And you could do it on an iPad.
Yeah, you can draw them on iPads.
Can you connect it to a system like Mathematica or something, which is better at doing visualizations and stuff like that?
No, we haven't done any study on that. The only other technology that I've worked with is a computer-aided system like Stack, which are my other research interest is assessment. So, but we only focus on this.
Well, I think already the widgets you can do in Lean, like the Rubik's Cube, I mean, this stuff is amazing. So you can, if you put in the work, you can have incredible visualizations.
Thanks for this. I think it's a really interesting question how students of exactly the demographic you're describing, which are sort of the intro to proof students who might need help in an intro to proofs course, how their experience with this tool translates to sort of pen and paper proofs later. But there's a dimension that I'm also curious about because if they're using Lean specifically and maybe some of the other proof assistants you mentioned as well, they're also learning mathematics in a different formal system, dependent type theory, than the formal system that will implicitly be used in the rest of their undergraduate mathematics curriculum, at least today. So in the future, Alex pointed out that our students should be learning, dependent type theory instead of set theory. But I'm wondering if you've explored sort of that dimension. If they're learning about mathematical objects in terms of types, and in particular with the existence of, or the sort of different treatment of equality in Lean, which is sort of quite different than how it's thought about in pen and paper. Have you explored sort of how that translates to giving communication with an instructor in a later course?
So the students we worked with were first-year students, and I believe that they didn't really appreciate this. I think I was talking to Kevin, you told me students don't really know in the first year that there's type theory underneath rather than set theory. So for the...
I try and hide it.
My experience is it's completely irrelevant.
Yeah.
Completely irrelevant. They don't see any difference.
But Patrick is doing the real numbers.
Yeah.
The real numbers and the natural numbers are these concrete types, and the fact that they're types, not sets.
Well, what about the identity type? I mean, that's the one that I'm really curious about.
What are the identity types?
Like the identity in the set theory, say the identity function is some subset of the diagonal. I mean, it's the diagonal.
Well, I mean to prove a proposition, you're constructing a proposition involving equality in Lean. I'm not talking about hot identity types, like Lean identity types. To prove a proposition, you're constructing a term in the identity type. I mean, I don't know. That feels different to me. I don't know how you hide that from the students, or if you'd want to hide that from the students.
I try and hide it, definitely.
But there's nothing to do, it's just hidden by default.
I don't think I'd say the word type once in the natural number game.
Yeah.
I mean, in this implementation, students don't see this, right? So they don't realize that they're not conscious that there is a different system underneath in this first year of very basic things that we get them to do. Right? Obviously, later on it's a completely
It might depend on the kind of questions that you're showing the students. If I'm just trying to teach them about induction.
Well, I'm at the level of the natural numbers game, so we're not doing any more complicated mathematics, but
But this is not complicated mathematics, but it's somehow completely different to the natural number game, right? This is, yeah, I don't know.
Well, because there's no equality. I feel like the equality is the confusing thing.
They already know what equality means. I mean, they think they know.
They don't know what's equality of
No, we
types.
don't know what.
but that's
I mean, there is also, I mean, there is also all this other kind of thing at the bottom. So we think students reason about equalities like we reason about equality. It turns out that they don't. And there is an enormous literature about how students, even at the university level, reason about equality, which is not what they should be doing. So we assume, so sometimes some of the issues of this research that we do is that we assume that the students think like we think, right? And so they are careful with all these details and they understand about all these meanings of equality and so on. The reality is that at this level they don't, right? So it's probably, as I said, I've never had a student that's engaged with this. And we've done some more data collection after this. Chiara has done lean workshops where she's recorded with students' activity and so on. It's never come up that somebody said, wait, I can't do this because this is an equality in type theory.
But Emily, let me make a confession to you. So I taught this Intro to Proof class in 2016, and I've taught it for 5 years as well in the early 2000s. And I started using Lean, and I thought, there is nothing that this software can teach me that I don't know already about it. Like everything about this course, I know and understand completely, having taught it 5 times. And then I ran into propositional extensionality and realized that I was completely confused about the concept of what it meant for the difference between 2 propositions being logically equivalent and being equal. And I realized I'd read the definition of what it meant for 2 sets to be equal, and I had no idea of what it meant for 2 propositions to be equal. And so if I don't understand equality, and I'm teaching these people year after year, then I'm sure that they just end up as confused. They just end up not. You're seeing subtleties that me as a teacher was completely unaware of until I started actually formalizing. So I wonder whether that's what's happening in a lot of places. People are unaware that there are complicated questions there, and so they're just hidden because nobody even notices that the identity type is something that you can actually say interesting things about.
I mean, so maybe I'm wrong to focus too much on the identity type. So you're talking about identity types in universes, which is a more complicated thing. But even just sort of propositions as types. I mean, I feel like when I've tried to introduce mathematicians to the natural numbers game, there's, you have to sort of explicitly explain that to prove a proposition, you're constructing a term at a type, which is a totally new idea. And so I'm curious.
But I don't say that. I say with great theory. It's a secret.
Yeah, well, so Emily, I have the same question. So why can't you just say to prove this equality, you just have to calculate, and here's how you calculate. You can substitute this when you know this is equal to that. You can do the substitution. I mean, you have the rules for equality. You have the reasoning rules. Just say this is what it means to prove a theorem. Why do you need to wrap it up in this metaphysical discussion of happening identity types?
I think one of the reasons natural number game is successful is to hide everything. It's all
I mean, the foundation should be invisible, right? I mean, we're teaching mathematical reasoning. And mathematical reasoning, it's just here's how you do it.
Yeah, I mean, at least at this level, right? Obviously, later on, you become an expert, but.
I mean, do students ever wonder about, sort of like the relationship between, P implies Q and Q implies R implies P implies R and composition? Does anybody notice that that's the same?
I think the ones that notice are the ones that start coming to the Lean Club, and then the next thing you know, they're improving in Lean, and then they actually find out what's going on.
When we talk about the foundations of mathematics, I mean, we should remember that the foundations are below ground, right? I mean, we do mathematics here, right? And when you want to go down to the basement and see the machinery and see what's working, it's down there. So, I mean, I think it's there. It's something that students can learn and may be interested in exploring, but it's not at the ground level. They don't have to start with that.
When you see a house, you don't check the plumbing first thing.
There's also another.
But why do you want people to learn dependent type theory then? If everybody's saying this, well, I mean, I'm sold. I want people.
Okay, so I was given a set theory course and told that this is how we do things, and then the very next class it was like, oh, by the way, that was a lie. We just do math. And then I was like, okay, so we have to pay lip service to the fact that there are these foundational issues. There is plumbing in the building that makes the whole thing work, but don't ever look at the plumbing. Just work, go to the second floor, go to the attic.
there is also another component, right? So I have 285 students, first-year students in my class. If in 10 years' time, one of the students will be sitting in a meeting like this, I'd be lucky. I want all my students to learn some mathematical reasoning because that is very useful in a lot of ways. The students that then go to the Lean Club that Kevin runs and they're all now doing postdocs, that's great. These are the ones that then will come up and say, oh, but I did not thought about it. So
you did make a point in one of your slides that the students kind of get the hang of what the lecturer is expecting the solutions to be.
Yeah.
So they write in the style of the lecturer. And my understanding is that it might even mean they write in different styles when they're doing different exams.
Oh yeah, so in a completely separate studies, we see a very big difference if we ask students to write a proof and we ask students to write a proof that will be in an exam paper so that they will be assessed. Yeah, but this is not surprising, right? My job as a student is to try to do as well as I can, right? So no students enter university with the idea of being kicked out at the end of first year, hopefully. And so I'm trying to understand what I need to do in order to do as best as I can. And this is really quite obvious. In fact, on studies that talk about students' reasoning, mathematical writing, and so on and so forth, and they have data which was collected from an exam, we always ask the question, have you considered the fact that this is an exam? And the students may write differently, different things, longer, this thing. So this is quite a well-known effect.
I suppose, so I infected some of these students with the Lean way of thinking when they were first years. Then they went to second year complex analysis. and they were showing this proof that if you integrate around this contour and then around this smaller contour, then the answer is 0. And the proof is you draw a big oval and a little oval, and a line between them, and then you sort of trace out this thing. And they came back and reported to me that this is what their second year analysis lecturer was telling them. This is clearly meaningless argument. And then they, but of course, when they come to the exam, that's exactly the picture they're going to draw.
We had Paul, Christian.
I guess I want to ask, do you have recommendations to make to the developer community for how they should be making their systems better for teaching?
Well, I think that's, so there are some small things that are happening. So there is a growing group of people like myself who thinks about learning that are interacting with people that use this for teaching. So there is some sort of exchange of ideas and so on and so forth. My end game would be to give somebody who is developing a course in first year to use Lean to have an idea of things that may be suitable and things that may work according to what they want this course to do, because this is also a different thing. So there are community we try to write on professional journals. So I have a piece in the Notices of the American Mathematical Society coming out in August that talks pretty much about these things, and this is a way to get in touch. So we try to work collaboratively. That's my approach. We don't have recipes, so education doesn't work like this. We can tell you, you go away, you do this, and this will work, because it depends on your students, it depends on the context, it depends on what aim you have. But we try to give indications of what has worked in certain contexts so that people can then think about them and use them in their own teaching. And hopefully we'll also get to the stage of developing resources and evaluating them.
Can I ask a really stupid question? So, for those of us who I'm not looking to become an education researcher, but I'm interested in these questions and I want to implement them in my classroom. So, is there some kind of data that would be useful to you if people like me collected information?
Oh, how long do you have? Yes, there is.
Very little.
Oh gosh, okay. Now there is all sorts of data. Just even talking to you and kind of seeing what you are doing and the material that you are using and what is your experience is useful to us. I mean, obviously we have our own practice, but I don't have access to what everybody else does. So, and then after that, we talk about study design and see what kind of questions we're trying to ask to what end we want. So, for example, sometimes we ask people to look at exam papers if you want to look at writing. I am at the University of Edinburgh, all exams now, the students are allowed to bring in a piece of paper where they've written notes, 2 sides of A4, I'm doing with the manual students next year. I'm doing a study collecting all these pieces of paper and doing a categorization of what is that the students actually bring in. Because we all think we do this because then it focuses them on the important part of the course. It turns out that a lot of them are made up of fast solutions or exam papers. So it depends a little bit what we do. So if you're interested in talking, yeah, please get in touch. There is.
My question is about motivation. Very often general public and students ask, why do they need to learn how to prove theorems if machines do that?
I don't know that the general public know the machine can do it yet. So.
They heard somewhere. You see, I'm sort of active in public communication about mathematics, and many people say that. Even high school students don't need mathematics because machines do that.
I don't know. I mean, the standard answer that you would get from somebody working in the UK would be that mathematics is useful anyway. So you need to do mathematics because you need to do your bank balance and you need to do all these things. This is the standard kind of utilitarian explanation of why we still need to do mathematics. And there's no point if I cannot do something quickly just when I look at something and I need to pull out lean because I don't always have. So this is more generally, I mean, it's got to do with what we want our society to do and why we think mathematics is important. But I think that, I don't know, I've never heard this. Nobody's ever come to me and said, you know, we have theorem provers, why do we need to do that?
Because mathematicians are as well placed to answer this question as anyone, since it's been an issue for us for 80 years. Calculators have been around, and
but we still
to know their times table.
Yeah, but we still teach students to do mental arithmetic in a primary school.
Exactly.
So would you advocate that we need to stop doing that?
Absolutely not.
Exactly. So it's a little bit at this level, not at this level. It's a little bit the same conversation. Okay, I'm going to go because otherwise panel will not get.
Thank you very much.